All right, hello everyone. Today we're solving LeetCode 116, populating next right pointers in each node. We're given a perfect binary tree, and we want to set all nodes' next pointers to the node directly to the right. And if there is no node directly to the right, we want to set it to null. And initially, all next pointers are set to null. All right. So in figure A, we have an example of the tree before we set its pointers, and this is what the tree should look like after. One key thing to notice is that all next pointers are initially pointed to null. So that means that all the last nodes in every level are actually already set accordingly because there is no right node. So they're initially set to null, which is correct. So we actually don't have to touch them. And for the rest of the nodes, all we need to do is a breadth first search traversal because it's level order. And we're going to set its next pointer to the next node in the queue. And if that doesn't make sense, that's totally fine. We're going to quickly go over it. So in breadth first search, we have a queue, and I'll just draw it here as like an array. And remember, we always start at the root node. So we have the node 1. Now we iterate over the queue or the length of the queue. So in this case, the length of the queue is 1. So we pop off the 1 and we say, hey, is this the last node in the level? There's only one node in the first level, so we don't do anything. It's already pointing to null. Right. Next, we append its children. So we say, does it have a left and right? It does. So we will append 2 and 3. And now we iterate again. Now we want to iterate through all the nodes in the queue. In this case, it's going to be 2. So we're going to go 2 times. And now we're going to pop off the 2. And we say, hey, is this the last node in the level? It's not. 3 would be the last node in this level. So we set its next pointer to whatever the next node is in the queue. The only node available in the queue now is 3. So we want to set 2's, which is our current node, next pointer to the first node in the queue. So that would be 3. So now 2 points to 3, right? We iterated once. So now we have to add its children to the queue. So we have 4 and 5. These are 2's children. And we iterated once. So now we have to iterate one more time in our for loop. So we pop off the 3. We say, hey, is this the last node on the level? It is. So we don't have to do anything because it already points to null. And we just append its children. So we have 6, 7. Now the queue isn't empty, so we iterate again and we say, how long is the queue? It's 4. So we're going to make sure to iterate 4 times for every element in the queue. We pop off the 4 and we say, is this the last element in this level? It's not. 7 would be. So we set 4's next pointer to whatever the next node is in the queue. In this case, it would be 5. So now 4 points to 5. Right? 4 doesn't have any children, so it's fully been processed. So we continue. We pop off the 5. 5 is not the last node in the level. So we point it to the next node in the queue, which would be 6. It doesn't have any children, so we continue. We pop off the 6 and we say, hey, is this the last node in the level? It's not. So we set it to the next node in our queue, which is the 7. And now finally we pop off the 7. 7 is the last node in the queue and it doesn't have any children. So we are done. And as you remember, all nodes are initially pointed to null. So this 7 actually has a null already. And we just return root because this tree has been fully processed and all nodes next pointers point to the node directly to the right. And if there is no node directly to the right, it points to null. All right, so hopefully that makes sense. I'm going to show you how to bring this solution to life in code. So first, what I like to do is take care of a base case. So let's say they give us an empty root or empty binary tree. We say if not root, return none. Now we want to start our BFS. So I like to call it Q equals deque, and we're going to put the root inside for the first node, right? So the root would be 1 in this case. Next, we want to go until the queue is empty. So we say while queue. So this will continue until we have processed all nodes. Next, we need to know how many nodes are we going to process. So we need to know the size of the queue. So we have a variable called size. Size equals length of queue. And we're doing this so we know when we're at the last node in the queue, right? Because as you remember, we don't want to set 7's next pointer to anything because it's already correctly set. And we need to have the size to know when we're at the end of the level. Next, we want to iterate through our queue. So for I in range length, or I in range size. So it's going to loop through the size of the queue. And if I is not equal to size minus 1, so all this is saying, if the current node that we are at is not equal to the last node in the level, we want to set its next pointer to the first element in the queue. All right. So how do we get the first node? We need to pop off the queue. Just like when we're here, we're Xing them off. To do this in code, we'd say q.pop left. So that gives us a node, and now we have to assign it to a variable. So we say node equals q.pop left. Now, if the current node we're at is not the last node, we say node.next equals q at index 0. So the first node or the next node that is going to be in queued. And now we want to append the children. So we say if node.left q.append node.left, and we want to append node.right. All right, and that's literally the entire solution. Now all we have to do is just return root. So return root, and let's try it out and see if it works. There we go. We've solved the problem, and it's actually very efficient. It beats 90% of runtime and 98% of memory. And if you enjoyed this solution, please drop a like. And if you have any questions, comment down below. Peace.